Hello everyone. So previously we found zeros of a function whenever the function was factored or could easily be factored. The question might be, well, what if the function isn't factored or easily factorable? How can we find the zeros of the polynomial function? Because remember, if a function is in factored form by zero factor property, we can set each factor equal to 0 and find the solution to the polynomial equation set equal to 0. So let me recall something here. I'm just simply going to recall something from before. Recall that if, this is when we talked about zeros, real zeros of a function. So recall that if r is a 0, and we're going to say that's a 0 in the form x minus r. So if it's a 0, then x minus r is a factor of the polynomial function. Okay. And we can also say that r is a solution. True, it's a solution to f of x equals 0. So we've talked about this previously in great length. Now, let's take a look at a more general form of our division. What if I'm dividing, let's say, f of x by, let me go g of x. If I go f of x divided by g of x, well, usually when we divide polynomials, we can do long division, just like we do with numbers. Now, to remind how we do long division with numbers, suppose I want to divide 15 by 2. Well, we can set it up in long division in this form. And remember, 15 is called, again, a dividend. And a 2, which is the denominator, is called a divisor in the long division. So 15 divided by 2, we're going to go 7 times 2, 14. Then we subtract, and the remainder is 1. Remainder, and 7 is what we call the quotient. Now, once we have this, we can actually write the division of 15 by 2 as 7 and a remainder of 1 divided by divisor, right? So 15 divided by 2 is going to be 7 and 1/2. Now, the same structure holds when we divide polynomial functions. Okay, so let's say I'm going to divide f of x by g of x. Well, if we do that using long division, the result's going to be q, which is the quotient, plus a remainder, possibly as a function of x, over the divisor g of x. So it follows exactly same structure as it does with numbers. Now, if I multiply both sides of this expression, the one on the left, this one, by g of x, then we get f of x is equal to q of x times g of x plus a remainder. And this is the form that we like. And it's important. It's really important what this form's telling us. This is telling us that every function can be written as a product of two other functions plus a remainder. Okay, and of course, when we do this in this work, the degree of the remainder is going to be less than the degree of the divisor. Okay, and that's by virtue of long division. That's why it is. Now, to show an example of this one, let's do a long division. Suppose I want to divide x squared plus 2x minus 6. Let's say I want to divide this by x minus 2. Okay, so to do this one using long division, we're going to write x squared plus 2x minus 6. Here's our dividend. The divisor is x minus 2. Now we divide the first term in here in the dividend by first term in the divisor. X squared by x, and that would be just x. That is the first term in the quotient. We then multiply x times x minus 2. We get x squared minus 2x. And just like with the number part, remember the next step is to subtract So we're going to subtract the bottom polynomial for the one above. And to subtract is to change sign on these two terms and add them. First we have a pair of opposites, and then we have 2x and 2x makes 4x. Bring down the 6 and continue on. Okay, and there we go. Now this is like our new dividend. So we're going to divide now 4x first term by x. We get 4. And then we're going to distribute 4 to the divisor, and we get 4x minus 8. Subtract, which means change signs and add them. We get a pair of opposites. Negative 6 plus 8 will be a 2. And this is the remainder. And notice the degree of this polynomial in the remainder, which is, I know it's a constant, but we can think of it as a polynomial. This a number in terms of polynomials is a polynomial whose degree is 0. And look at the degree of the divisor. The degree of the divisor is 1. So this is how this algorithmic process stops when the degree of the remainder, when the degree of the remainder is less than the degree of the divisor. That's when we stop this long division algorithm. And at this point we can write this as the ratio of a quotient. The ratio is a quotient plus a remainder over a divisor, and that's precisely in this form. Now if we can multiply both sides by x minus 2, we can say that x squared plus 2x minus 6 is equal to x plus 4 times x minus 2 plus a remainder. That's also true. That's going to this form, to that version. Okay, now we're going to come across a theorem. Hopefully you followed what I said there with this example. Let's talk about the remainder theorem. And I'm going to write this theorem, and then I'll come back and talk about it. Okay, so here's the remainder theorem. The remainder theorem says if a polynomial function is divided by a binomial, and notice it has to be in this form, everyone, x minus c. There has to be a minus between x and c. Divided by x minus c, and then the remainder in that division, because we're dividing in that remainder, the remainder is f at c, which is the value of the function at c, which is interesting. The remainder theorem will actually helps us evaluate functions at a point by doing actually a long division. Okay, now we may not want to do it that way, but it allows us to do that, and we'll see an example of how this could be beneficial in a moment. So we can actually prove this thing. The proof isn't too bad. Remember, we can say f of x is equal to, we're dividing by x minus c, so x minus c is a divisor, and then remember a quotient plus a remainder, right? And that's r of x. That's our remainder. Now at x equals c, because we're dividing by x minus c, so at x equals c, you just change x to c, and this is going to be, well, instead of x now we have a c, correct? That's going to be a c minus c times q quotient at c plus a remainder at c. Of course, this would be 0 because c minus c, 0 times anything is 0. Now the remainder at c here, because we're dividing by a binomial, up here I said the degree of the remainder is less than the degree of divisor. Your divisor is x minus c. Okay, well, the degree of x minus c, this one has a degree equal 1. So that means r at c is going to have a degree that is less than that. Well, less than that means 0. And if the degree of a term is 0, that means this is a constant. That means r at c is a constant. Well, R at C is a constant, so we just said that F at C is equal to a constant here, right? And that's the remainder at C. Okay, that's exactly what that remainder is. Therefore, we can say that F at X is equal to X minus C times the quotient plus F at C. All right, and there you have it. So this is what the remainder theorem tells us. Okay. Now a consequence of remainder theorem is also another important theorem called factor theorem. Okay, so let me write that theorem for you and then we'll talk about it. Okay, now this is pretty much the factor theorem. So the factor theorem goes like this. The actual theorem, this is kind of like the proof of it. Okay, the factor theorem says that X minus C is a factor of a polynomial function. Call it f of x if and only if f at c equals 0. Now, the reason the factor theorem works is this. Remember the general form of all functions. We can write them like this. And polynomial function, that is, we can write them like this. Now, if f at c is 0, then, well, this part is 0, correct? So the expression reduces to what you're seeing here. And that would imply, because x minus c multiplies by q of x, the quotient, then that would imply x minus c has to be a factor of the polynomial. Now this has really far-reaching consequences. If x minus c is a factor, that's good, because now we're able to find the zeros of a function, and that's always good to know and be able to do for our work. So the factor theorem, therefore, it goes like this. X minus c is a factor of a polynomial if and only if the remainder of f at c is equal to 0. Okay, now when we say if and only if, that means this theorem has two parts. The first part says if f at c is equal to 0, then that would imply that x minus c is a factor, which is what I showed just up here, right? See, if f at c equals 0, we just show that x minus c is a factor of f of x. That's the first part. Now, because of the only if, what this will do is creates a bidirectional implication. Okay, and for that, the second part of this theorem goes like this. If x minus c is a factor of f of x, then f at c must be 0. Okay. Now again, the proof, I just rewrote the if and only if statement of the theorem as two statements. Okay. Now, to prove this, we can easily prove it. Okay, so the proof for part 1 is this. Well, f at c, if f at c is 0, so we take that to be true. That's a given part. That's called the hypothesis of the theorem. Well, if f at c equals 0, then we just showed up here, we show that f of x is x minus c times q of x, and that would imply x minus c is a factor. Something, again, I showed above. To prove part 2 of this theorem, to prove part 2 now, if x minus c is a factor, we are given that now. That becomes the hypothesis of the theorem. So if that is a factor of f of x, well, then that means the quotient q of x exists, right? It exists, and f of x can be written as x minus c times q of x, because we're told, we're assuming x minus c is a factor, so f of x can be written in this form. Okay, now replace x by c. Replace x by c, and this is what we get. We get f at c is equal to c minus c q. Okay, sorry. And let's write that as q at q of x, but then replace x by c. So let me just put qc. There you go. And that's going to be 0 because that is 0. So we just showed f at c must be 0. And that is actually the proof of the factor theorem. Again, you're not responsible for the proof, but it's good to see that this theorem works. So again, the takeaway is this. X minus c is a factor, then we can write a polynomial in this form. And f at c must be 0. So let's take a look at an example, how we can use this. So I'm going to make up a polynomial. Suppose f of x is 5x to the 4th, negative 20x cubed plus x minus 4. Okay. And we want to find the remainder. Okay. So let's say we want to find the remainder when f of x is divided by x minus 2. All right, so that's what we want to do. In this case, c is 2 now. Okay, so to find the remainder, we just have to do f at 2. And f at 2 would be 5 times 2 to the 4th, negative 20 times 2 cubed, plus 2 minus 4. See that? So we don't have to do long division. That's the whole point. And there you go. There's your remainder. The remainder is going to be negative 82. Okay. Now, is x minus 2 a factor as a result of this? Let's pose that question based on what you just observed. Can I say x minus 2 is x minus 2 a factor of f of x? Well, to be a factor, remember by factor theorem, f at c has to be 0, right? So we can say that by factor theorem, no. The answer is no, because f at 2 is not 0, and that's why. The remainder has to be 0 for x minus c to be a factor. Let's take a look at another example. In this example, let's say f of x is 2x to the 6th plus 129x cubed plus 64. And this time, let's say we want to know if x plus 4 is a factor. There you go, x plus 4, a factor. Let's see if it is. So what are we going to do? We're going to find the remainder. We're hoping the remainder is 0, right? The remainder of f at negative 4. Because remember, x minus negative 4. It has to be in the form of x minus c. Okay, and so c here is negative 4. That's how I came up with negative 4 here. So f at negative 4, what is f at negative 4? Well, that's when we plug in negative 4. Let me move this a little lower. So it's going to be f at negative 4. And that would be 2 times negative 4 to the 6th plus 129 times negative 4 cubed plus 64. Okay, now if you do the arithmetic of this, I've done, and let's see, I think I got 0. Okay, I'm pretty sure, but you might want to verify this. So that's what That's what I got. Therefore, since f at c equals 0, then that means x minus c is a factor by factor theorem. Okay, so I'm just going to cite that by factor theorem. Since f at -4 equals 0, that would imply x plus 4 is indeed a factor of the polynomial. And that's good again, folks. If we have factored form, that's excellent. Because to solve equations, we really need them to be factorable at this point in our work. Okay. Now, let's take a look at another theorem. Okay, this next theorem tells us about the number of zeros, real zeros. Okay, so I'm going to put a couple of theorem for you, and then I'll continue on. Okay, so here it is. This first theorem we're going to look at gives you the number of real zeros, which are solutions to f of x equals 0. So the first theorem says a polynomial function cannot have more real zeros than its degree. That's why the degree of a polynomial, again, is very important in this work. So for instance, let's say we have a 4th degree polynomial. Well, according to this theorem, it cannot have more than 4 real zeros. You have a 3rd degree, you cannot have more than 3 real zeros. That's what that one is. The next theorem actually finds or tries to find rational zeros. Okay, now remember, rational numbers, these are like your fractions. Remember, a rational number is a number in the form p over q, such that p and q are integers. Okay, and q cannot be 0. So all your fractions are, in other words, rational numbers. Sorry, I left the word rational, left the L out. So we're talking about the rational zeros. Example, rational numbers: 2/3, 1/2. Even whole numbers, like 5 is a rational number. I can write it as a ratio of 2 integers. So these are all rational numbers. And of course, terminating decimals. Remember, this goes back to pre-algebra. If a number is terminating decimal, it's rational. If it's non-terminating decimal, but it has repeating blocks of digits, it's rational. But if it's non-terminating, non-repeating blocks of digits, then it is irrational. Example of irrational numbers are like square root of 5, pi, e, things like that. Those are all irrational numbers. Okay, so we're talking about numbers that are at most fractions or terminating decimals, or non-terminating, like 2/3, for example. 2/3 is non-terminating, right? Decimal, and the digits continue on is 0.666666, like that. So those are what we mean by rational numbers. Now, the theorem, very interesting. Here's how the theorem works. The theorem reads, let the function be a polynomial function of degree at least 1. At least 1. And what I have here is the general form of that rational function, right? F of x is equal to a sub n times x to the n plus all the way down to the constant. Now those coefficients must be integers, and I just have a review of integer numbers there for you. These are your counting numbers, like 1, 2, 3, and their opposites, -1, -2, -3, and so on, including 0. Okay, now, if p over q, and p over q must be in lowest terms, means simplified. Okay, it has to be simplified. So if p over q is in lowest terms, and suppose p over q, that fraction, is a rational 0, like I mentioned earlier, like I have up here. These the numbers that are like these, rational zeros like those. Okay, remember, these are irrationals. If it's rational zeros, then p, the numerator of this fraction, must be a factor of the constant, and q must be a factor of the leading coefficient. Okay. And that's what the theorem says. Now, it's important, a couple of important notes here I have. One is that the theorem doesn't actually reveal, it does not reveal irrational zeros. Okay, so it doesn't tell us about irrational zeros. That means if, for example, pi is a solution, this theorem doesn't do it. If square root of 2 is a solution, this theorem won't work. Okay, it won't give us those. So that's our first note. The other note is that the theorem gives what we call potential solutions. These have the potential to be zeros. They may not actually be solutions. Okay, solutions. Okay, so we just want to clarify this. And that's it. That's what the theorem tells us. So let's see how we're going to actually work this theorem and see how we can use it to find zeros of polynomials. So in my first example, we just want to list potential rational zeros just to practice with p and q here. So my polynomial is negative 9x cubed negative x squared plus x plus 3. And for this, that's all I want to do is just list potential rational zeros. That's all I want to do. Potential rational zeros. So we need to figure out p and q. Remember, p is made up of all factors of the constant. Well, factors of 3 are, well, 3 is prime, so 1 times 3, correct? Those are factors of 3. But for this work, we go plus or minus. And the reason, because negative 1 times negative 3, see, that's equal to 3. So is 1 times 3. So we need to pick negative as well as positive factors here. So, and hence we have plus minus. Q would be all factors of leading coefficient. That would be plus minus 1, plus minus 3, plus minus 9. So for example, negative 1 times 9 is negative 9. 1 times negative 9 is negative 9. 3 times negative 3 is negative 9. That's why we have all those plus minuses there. Okay, now once we have formulated or found P and Q, we need to take the ratio of those, P over Q. And P over Q, now I'm dividing plus minus 1 for P by each and every one of the Q's. So I get plus minus 1 divided by plus minus 1 is plus minus 1. Plus minus 1 divided by 3, that gives me 1/3. 1 divided by 9 gives me 1/9. And that's all possibilities with 1. We're going to repeat the same thing with 3. Plus minus 3 divided by plus minus 1. 3 divided by 1 is 3. 3 divided by 3 is 1. But then 1 is already accounted for, right? So we don't need to repeat that part. And 3 divided by 9 is 1/3. That already is in here as well. So we have completed the list of potential zeros. Again, this is a third degree polynomial, remember? So we can have at most 3 real zeros. So these are all potential. Notice I have a list of 4 times, so 8 numbers. All 8 of them are not going to work. And in fact, none of them might work. If the solution is rational, we are limited to these choices. But if the solution is irrational, again, this theorem does not help us at all. And there you have it, your potential zeros. Let's take a look at another example. And in this next example now, we want to actually find the real zeros. So let me do that. Find real, and the keyword here is real. If the solutions are, for example, complex, this won't help us because we're looking at a polynomial with real coefficients. And that's 2x cubed negative 4x squared negative 10x plus 20. So suppose I have this polynomial function. Okay, so Remember, p is all possible factors of the constant, 20. So that's going to be plus minus 1, plus minus 2. It's going to be a long list. Plus minus 4, 4 times 5 is 20, 2 by 10, 1 by 20. Look at all those. Q is all possible factors of the leading coefficient, the factors of 2, because 2 is prime. It's 1 by 2, 2 itself and 1. So that's just going to be plus minus 1, plus minus 2. Now, P over Q. Now we're going to have a long list, right? P over Q is going to be all of these divided by 1 and all of those divided by 2. So I'm just going to list them. Well, every one of these divided by 1 gives you those same numbers again. So I'm just going to copy them from P. That's when you divide each and every one of those by, oops, I have 2 here. That should be 10. I said 10 times 2, so I threw myself off. And this would be plus minus 10, plus minus 20. And there you have it. So those are all potential zeros when you divide by 1. Now we divide every one of those by 2. So here we go. 1 divided by 2. I'm dividing every one of these by 2. 1 by 2. That's 1/2. 2 by 2 is 1, but 1's already in here, so we don't need that one. 4/2, well, that's 2. It's already here. We don't need that one either. Okay. 5/2 plus minus 5/2. I didn't have that one. 10 divided by 2 is 5. We already have that. 20 by 2 is 10. We already have that. And there you go. This is the list of all candidates. Potential zeros. This is a third-degree polynomial. It has no more than 3 real solutions. And those 3, if all 3 are, which we don't know, if they are rational, it's going to be among these numbers. And we have to search and find them. Okay. Let's see. So how are we going to do this? Well, we need to try some of these, and it's just pure luck as far as which one you try and which one's going to be a solution. You can randomly pick any one of these potential zeros. Okay. Now usually we start with easy numbers like plus minus 1, plus minus 2. We are hoping that that itself will capture a 0, and then we go from there. And for this one, by the way, once we find the zeros, we're going to factor the function over the real numbers. So you see what the factored form will look like. Now, let me sidebar here. We talked about synthetic division. Okay, so let's do a synthetic division. The synthetic division is the result of dividing a polynomial by a binomial. Okay. Remember, when we said the factor is x minus c, this is a binomial factor, right? So it makes sense to do synthetic division here. Synthetic division. Synthetic division is a fast way of doing long division. So for example, let's say I want to divide 3x cubed negative 4x squared plus x minus 2. Suppose I want to divide this by x minus 3. Okay, let's see what's going to happen. How are we going to do this in synthetic division? So using synthetic division, this has nothing to do with what we're doing up here. Again, this is on the side. So for synthetic division, we're going to write all the numbers in the numerator, the coefficients in the numerator. So that's going to be 3, negative 4, 1, negative 2. If any term, by the way, is missing as you go from left to right in descending powers, we use 0 as a placeholder. And then in the denominator, x minus c. C here is 3, right? That's what c is. Minus is part of the form. Now here's how synthetic division works. We're going to bring down the first 3 in that column. Then we're going to multiply 3 by 3, we get 9. And we're going to add in column, we get 5. We then multiply 3 by 5. and get 15. And then we're going to add in column. That's 16. 3 times 16 is 48. And we're going to add in column 46. There you go. So if we do a synthetic division of what I have by x minus 3, this is going to be the quotient. And this is going to be the remainder. See how that works? It's pretty cool. Now, we are hoping when we do this, when we try to find real zeros, we're hoping the remainder will be 0, because remember the remainder theorem? If the remainder is 0, therefore x minus c is a factor. And a factor becomes a 0, right? Ultimately leads to a 0. So here's our guess and check part. So I'm going to guess at c equals 1. Okay? In other words, I'm thinking x minus 1 may be a factor. Let's do synthetic division. Now we're working with the actual function here in this example. I'm going to write the coefficients. Coefficients are 2, -4, -10, and 20. And c here, c is 1, correct? So c is 1, and let's do our long division here. Bring down the 2, multiply. Add -4 and 2, we get -2. Multiply. 1 minus 2 is -2. Add in column, -12. 1 times -12 is -12, plus 20 is 8. Not 0. If it's not 0, that means 1 is not a solution, or x minus 1 is not a factor. See how that works? Now look at this long but distinguished list. So potentially we could try a number of these and see if they work, correct? That's why it's really the luck of a draw, which one's going to work, which one is not going to work. But synthetic division is how we want to do this to make this go fast. Now, I've tried several of these, but let's try 2, because 2 worked. So here's how I'm going to do it. This is the first row of the synthetic division table. And this time I'm dividing by x minus 2. In other words, my c is 2 now, right? C is 2. So I'm thinking 2 is a real solution. It is in the list after all, right? Let's try 2. Bring down the column, bring down the 2, and multiply 2 by 2, 4. We get 0. 2 times 0 is 0. 0 minus 10 is -10. 2 times -10 is -20. You add in column, and we get, voila, there is 0. You see that? This tells me the remainder is 0. If the remainder is 0 by factor theorem, therefore x minus 2 is a factor. Now remember, this is the quotient. This is our quotient. And if you divide a third degree by a first degree x minus 1, the quotient would be a second degree. This quotient has a degree less than the original because we divided by a linear factor. So it's a second degree quotient. Second degree means polynomial. Now usually once we're down to a polynomial, we simply solve that polynomial expression. Okay, what does this polynomial expression look like? The 2 here means this is 2x squared plus 0x minus 10. That's what this quotient looks like. And of course 0x is just 0, so we don't write it. And at this point, set this equal to 0 and solve this. Instead of trying by trial and error, trying those other numbers. And you will see in the case that I have here, I could have gone through and literally tried each and every one of these, and none of them are going to work. Okay. Oh, another thing is, once you find one of the solutions, in this case 2, if the solution is repeated, if there's multiplicity of more than 1, You could try 2 again, and if it gives you 0, then you count that 2 twice. Okay, remember in factored form, it will be x minus 2 squared. If it works 3 times, then it's x minus 2 cubed in factored form. So it is possible. It is possible for a 0 to repeat itself. Now let me solve this last equation that we have here, this one. I'm going to divide everything by 2, so I go x squared minus 5 equals 0. Then move 5 to the other side. Take the square root of both sides. We get plus minus by square root principle. Check this out. See, square root of 5 is irrational. And your rational zero theorem doesn't say anything about plus minus root 5, right? Look at that list. It doesn't include plus minus root 5. Because these are quote-unquote rational zeros. Okay, well, we expect 3 solutions, so let's factor this. We found the solutions, by the way. The solutions are, the other one is x equals to 2. Those are the 3 solutions. 2 is the rational one. The other 2 are irrational. So in factored form, we have the leading coefficient, which is 2, right? This is your A. In factored form, the factored form for a third degree polynomial looks like this: x minus c1, x minus c2, x minus c3. Now earlier we used r, by the way, so that's fine. It's just a notation. That's exactly the same thing. So if you're wondering how come he's using c now, because your book does. And there you go. So those really mean the same thing. These are the zeros. Now finally, we can write the form. F of x is going to be a. Leading coefficient was up here. Again, it was a 2. Correct? So let's do that one. And that's going to be 2 times x minus 2, x minus square root of 5, and x plus square root of 5. 0, 0, 0. All right. And there's the factored form. Okay. Let's try another example. In this example, let's say f of x is going to be 4x to the 4th plus 5x cubed plus 9x squared plus 10x, and then plus 2. And we want to do the same thing. We're going to find the zeros. Okay. And let's see how this is going to work out. The rational zeros are, well, p. Remember, p is factor of the constant. That would be plus minus 1, plus minus 2. And q is going to be factor of the leading coefficient. Factors of 4 are 1, 2, and 4. The ratio of these two is the potential zeros. So 1 by 1, 1 is going to get divided by each and every one of these. So 1, 1/2, and 1 divided by 4 is 1/4. And then we're going to repeat the same thing with 2. 2 divided by each and every one of them. 2 by 1 is 2. 2 by 2 is 1. We already have that. 2 by 4 is 1/2. I already have that. So we are done with this work. These are all potential, again, rational zeros. So for this one, now let's try -1. Again, at this point, it's anybody's guess which is going to work, which is not going to work. None of them might work if all solutions are irrational. So let me choose -1. -1, I have the first row of the synthetic division table. You write all the coefficients. Now, for example, if 10x was missing, by the way, you should still write that, but you put a 0 there, okay? So we cannot skip, you cannot leave those columns blank for the missing terms. Bring down the 4, right? And the synthetic division algorithm kicks in. -1 by 4 is -4. Add -1 by 1 is going to be -1, and add -8, add negative 2, add, and there you go. Remainder is 0. Perfect. So that means we have one solution. So x minus negative 1, which makes x plus 1, is a factor. Negative 1 itself is a solution. Okay. Now, let me try and see if negative 1 works again. So here I have a hunch that there may be a repeated root. So I'm going to try negative 1 once again. Okay, I have nothing to lose if it doesn't work, right? Negative 1 by 4, negative 4, that's negative 3. Multiply, add, multiply, add. Nope. So I do not have a repeated 0. That only works first time. It did not work the second time. I do not have a repeated 0. So what do I do next? Well, again, I've tried several of these that didn't work. The one that worked was negative 1. Let me repeat the first row. Actually, not the first row. You could repeat, by the way, the first row, but let's stay with the third row in synthetic division. 4, 1, 8, 2. That one is easier to go to now. Okay. And this time I'm going to try negative 1 quarter. Bring down the 4. 4 times a quarter is 1, except negative 1 gives you 0. Negative 1 quarter times 0 is 0. Add in columns. Negative a quarter of 8 is negative 2, and add, you get 0. There you go. So we found another 0. And this is another solution. We found the second one, right? Now, look at the third row in synthetic division. We started with the 4th degree, right? 4th degree. So this quotient, this one would be a 3rd degree because we divided by a binomial. And then we reduced that one, reduce this one right in here. We reduced it to a new polynomial. This is like a new dividend. And this one would be a 2nd degree. Okay, so we started with the 4th degree, and now we are down to a 3rd degree in the first run of that table in this row. Okay, 3rd degree. And then we're down to a 2nd degree. Once we're down to a 2nd degree, this equation, the third row reads 4x squared plus 0x plus 8. Set it equal to 0. And then factor of 4, we get x squared plus 2 equals 0. Don't worry about 0x. You can divide both sides by 4. That gets rid of the 4. So at this point, we only have x squared plus 2 equals 0, right? Now the solution, check this out. Subtract 2 from both sides. Can I square a real number and get negative? This can't be. Not real. And we are looking for real solutions. Okay. Therefore, the only real solutions. So here we're going to say the real solutions are simply a negative 1 and negative 1 quarter. Negative 1, negative 1 quarter. That's it. The other two solutions are not going to be real. They're not going to come from here as a real. There are yet 2 other solutions, but they're not real. And they end up being complex, and that's what we do in the next and the last section of this chapter. So now let's write the factored form. Okay, the factored form of the polynomial. So f of x can be written as x plus 1, x plus 1 quarter, right? It's x minus c. So I accounted for these two, and simply what's in the third row. And that third row, remember, it was 4x squared plus 8. And there you have it. Now make sure you carry the third row that has a 4. Don't look at this version that I divided the 4 out in the equation. Now, from the last binomial, I can factor a 4. And when I do, this is the final factorization of that function, polynomial function. That's going to be x squared plus 2. I factored the 4 from 4x squared and 8. Okay, and there you go. This is the leading coefficient a sub n. All right, and there we have that one. So we are able to write the full factorization of this polynomial. Okay. Now we're going to finish this work with another theorem, our last theorem, which is the intermediate value theorem. It's a rather easy one. So let me write it and then I'll come back and explain it. Okay, so here it is, the intermediate value theorem. The intermediate value theorem goes like this. Suppose we have a polynomial function. Let f of x be a polynomial function. And suppose we have two numbers here, a and b, where a is less than b. Now, if you evaluate the polynomial function at a, that's f at a, and evaluate it at b, that would be f at b. So you evaluate the functions at a and b. And if those two numbers that we evaluate, the y values, if they have opposite signs, so one is positive, one negative, doesn't matter which one, as long as they're opposite in sign, then there is at least one. Notice how this is stated. At least one means it could be one or more real zeros between a and b. Okay, so to kind of give you some like a sketch of what's going on in here. Let's say I have, and there you have it. Here's A and here's B. So this would be f at A, and this would be right in here, that's f at B. Clearly f at B here is negative, right? Because it's below the x-axis. And over here it's positive, right? Because I'm above the x-axis. Now in between, there's going to be at least one real zero. Check this out. There's one here, one here, one here, one here, and one in here. So this one I just made up has 1, 2, 3, 4, 5 zeros. And that's why the intermediate value theorem says at least one. And that's a sketch of that theorem, what the theorem says. So let's try it for this made-up example of mine. And we want to show that there is a zero between -5 and -4. So we're going to do f at -5, and that's 2 times -5 cubed plus 6 times -5 squared, and -8 times -5 plus 2, and f at -5. This ends up being -58 if I calculated it correctly. And then let's do f at -4. F at -4, again, the same process. 2 times -4 cubed plus 6 times -4 squared, and -8 times -4 plus 2. If I did the arithmetic of this one correct, I got that to be 2. So in the first one is negative, the second case is positive. Therefore, there is at least 1 0 between the closed interval from -5 to -4. Okay. And that's what the intermediate value theorem does for us. All right. And that should do it for us. I'm pretty much done with this section as well. We are almost done with this lengthy chapter on polynomial and rational functions. We only have one more lecture in this chapter, and that lecture will bring in complex zeros to our list of potential solutions or possible solutions for polynomial functions. So we'll talk about that one in our next lecture. Thank you for watching, everyone, and take care.